In the vast silence beyond our skies, entire worlds move in perfect balance. Planets trace invisible paths for billions of years without drifting into chaos. Gravity pulls, motion resists, and somewhere between them, a quiet harmony keeps the solar system alive and stable. Tonight, Space Dreams documentary journeys into the hidden architecture of orbit's resonances and the delicate forces that hold everything together. If the mysteries of deep space calm your mind and spark your curiosity, make sure to like the video and subscribe to Space Dreams documentary for more immersive explorations of the universe. Now let the journey begin. Above the sun's glare, paths appear that never settle into stillness, yet keep returning to the same dark lanes. Orbital stability comes from motion that continually balances inward pull with sideways sweep so a path can repeat for immense spans of time. A slow scene forms in a thin disk of dust and ice. Grains drift in wide circles. Faint bands begin to clear. The cleared lanes look like soft grooves in fog. The first quiet unlock sits inside that image. A stable orbit is not a frozen track. It is a living compromise renewed at every moment by speed and curvature. In that region, a small body does not hold on by effort. It remains because the rules of motion leave it no simpler way to go. Darkness deepens around the disk. The center is bright. The outer edge is dim. A gentle gradient appears across the material, thicker near the middle and thinner far away. That gradient matters. It hints that gravity sets a slope. Motion slides along that slope without falling straight down. Another image arrives. A planet becomes a small silhouette crossing a field of stars. The stars stay fixed in the background. The silhouette moves in a smooth arc. The arc repeats. The repeat is the second unlock. Stability is not perfect sameness. It is sameness within a boundary. The path can stretch and tilt. The timing can drift slightly. Yet the object still comes back to a familiar neighborhood in space. That boundary is drawn by energy and by turning. In that region, gravity bends the path inward. The sideways motion keeps the fall from becoming a plunge. Together they create a closed loop or a loop that almost closes and slowly precesses. A natural analogy sits beside the idea without importing human scenes. A leaf caught in a wide, slow eddy does not stop moving. It circles the same pool. The current pushes inward toward the eddy's center. The leaf's drift carries it around. The balance makes a pattern that can last until the water changes. The solar system holds countless versions of that quiet eddy. Some are tight and fast near the sun, some are broad and slow near the edge. A single safe number helps anchor the scale. A temperate orbit in the inner system takes about 1 year to complete a circuit like a slow wave that rises and returns on a steady tide. The tide comparison stays natural. It keeps the time tangible without pulling in clocks or calendars. The scale shift follows. A year is a brief heartbeat next to the age of the solar system. Over billions of years, the same orbit can repeat so many times that the count becomes more like sand than like steps. The third unlock arrives there. Stability is not measured by a single lap. It is tested by the accumulation of tiny differences across unimaginable repetition. The scene changes again. A belt of small bodies forms a hazy band. Each speck carries its own curve. Some curves are nearly circular, others are stretched into long ovals. The ovals have a closest point and a farthest point. Near the closest point, motion quickens. Far away, it slows. That change is not a choice. It is a requirement set by conserved turning. In that region, angular momentum is a stored swirl. It keeps the path from collapsing into the center. A simple image supports it. In a narrow whirlpool, floating foam speeds up near the drain and slows along the rim. The water's turning concentrates as the radius tightens. The foam traces the rule without any calculation. The fourth unlock hides inside that motion. The same force that pulls inward also makes the path curve. Curving is not a failure to escape. Curving is the orbit itself. Yet stability is not guaranteed everywhere. The solar system is not a silent machine with perfect gears. The next scene lays down a physical detail that can be seen even in imagination. A ring of debris shows sharp edges. Some regions are dense, other regions are thin. The thin places look like clean cuts. The boundary is not a wall. It is a statistical frontier where repeated tugs remove material over time. The idea opens gently. Orbits stay stable when small disturbances average out. Orbits weaken when disturbances arrive in step with the orbit's own rhythm. The fifth unlock follows. Repetition can protect. Repetition can also erode. A push that is tiny once can become decisive when it returns at the same phase again and again. The calmness of the night sky can hide that slow arithmetic. From a near view, the system looks still. From a far view, it is a web of interacting cycles. A scale shift carries the mind outward. Near the Sun, orbits are compact. Distances change quickly. Far out paths widen. The darkness between bodies grows. Motion slows until it feels almost suspended. Yet even there, the same principles apply. Curvature remains. Turning remains. Gravity weakens with distance but never becomes absent. The sixth unlock rests on that continuity. One set of rules spans from inner warmth to outer cold. Only the tempo changes. A limit of intuition arrives softly with a clear statement of what breaks. Stability cannot be seen directly across billions of years. No observation can watch every lap. Even the best measurements have finite resolution. Small errors in position and speed remain. In long-term prediction, those small errors can grow. In some regions, they grow slowly and remain bounded. In other regions, they grow faster and make the future path uncertain. The limitation is not only in instruments, it is also in models. When many bodies interact, equations produce behavior that can be exquisitely sensitive to initial conditions. The boundary between steady and chaotic motion can be thin. It can lie like a seam in the fabric of space. That seam is often traced indirectly. It is inferred from gaps in belts, from the clustering of stable families, and from the slow rotation of orbital shapes. The seventh unlock follows from the limit. Even without perfect foresight, stability leaves fingerprints. It carves structures. It sorts populations. It shapes which regions stay filled and which regions are swept clean. Another visual anchor settles in. A distant planet glows faintly. Around it, a few small moons move in layered planes. The planes are slightly tilted. The tilt creates shadows that shift across the planet's atmosphere. The shadows repeat in slow cycles. The repetition is comforting. It suggests order. Yet the tilts also hint at history. They imply past nudges. They imply resonant timing. They imply tides that damp some motions and preserve others. The eighth unlock is quiet but firm. Stability is not only about staying in place, it is about staying in a range of allowed shapes and orientations while influences keep arriving. A final natural analogy closes the loop without reusing earlier images. A dune ridge holds its form in a steady wind. Grains move constantly. The crest migrates slightly. The dune remains a dune because flow and gravity settle into a repeating pattern. Orbits behave in a related way. Matter moves, distances change, speeds change. The form persists because constraints keep reasserting themselves. The paragraph eases toward what comes next. The next step is to name the central sculptor more clearly. Gravity becomes the quiet slope that all these paths follow, and the reasons for the slope begin to unfold. The curve of an orbit begins as a quiet answer to a simple pull. Gravity shapes the path by bending straight motion into a repeated arc. At this distance, a calm scene hangs in a wide plain of dust. The disk looks thin as a sheet. It holds a faint gradient from bright inner glare to dim outer haze. In that soft slope, material does not drift randomly. It gathers into lanes where motion can repeat. The first unlock arrives early. Gravity does not drag an object along a track. It continuously changes the direction of motion. The speed can remain. The direction turns. A clean curve appears from that turning. Another image settles closer. A single small body glides through darkness. The body leaves no mark. Yet the path is visible in imagination as a ribbon of repeated positions. Near the central mass, the ribbon tightens. Farther out, it loosens. The ribbon's inner edge looks sharper. Its outer edge looks softer. That physical boundary matters. It shows that a gentle change in distance changes the strength of gravity. The strength falls with distance. The fall is steep. The second unlock follows. Orbits exist because gravity weakens outward. If gravity stayed equally strong everywhere, stable loops would be rare. The weakening creates a natural balance point between staying near and drifting away. A new concept enters in plain language. A gravitational field is a map of pull strength in space. The field is not a substance. It is a description of how motion would curve at each place. 2 sentences of imagery carry it. In a shallow bowl, a marble rolls faster where the bowl steepens. It rolls slower where the bowl flattens. The importance lands quietly. The field's changing steepness is what makes some distances stable and others fragile. A fresh visual anchor appears. A shadow line stretches across a ring. One side is lit. The other side fades into a soft penumbra. The ring's particles do not move as a single sheet. Each grain follows its own orbit. Together they form a band with a crisp inner rim. The rim stays crisp because gravity and motion keep feeding the same lanes. The third unlock appears in that crispness. Stability is often visible as edges. A stable region keeps its boundaries sharp because long-term motion sorts what can remain. A simple everyday analogy supports the sorting without repeating earlier images. In a slow river bend, heavier pebbles settle where flow slackens. Finer silt drifts farther before it drops. Over time, the river makes layers. The solar system makes layers too. The layering is in distance and in speed. The layer is not a wall. It is a preference created by the field. A single safe number anchors the scale. At about 100 kilometers above a dense world, a low orbit would complete a loop in roughly 90 minutes, like a gentle cycle of breathing that rises and falls again. The comparison stays soft. It keeps the time relatable without pulling in schedules. The scale shift follows. 90 minutes is brief. The same gravitational rule also shapes paths that take hundreds of years in the outer darkness. The tempo changes. The curvature rule does not. The next scene moves outward. A distant planet appears as a dim disk. Around it, faint moons trace paths in slightly different planes. The planes form thin tilted sheets. Where 2 sheets cross a line of nodes forms. That line is a physical detail in geometry. It is a seam where crossings repeat. The 4th unlock arrives there. Gravity does not act only from the centre. Every mass adds a small bend, yet most bends average into slow, smooth changes rather than sudden breaks. The averaging happens because the main pull dominates. The smaller pulls arrive at many phases and cancel in part. Another analogy offers a gentle grasp. A bell hung in still air sways in a clean arc. A faint breeze pushes at random times. The sway remains. The arc slowly shifts. The motion stays bounded because the pushes do not repeat in perfect step. The section leans into a deeper point without sharpness. Gravity is not only a force, it is a geometry of acceleration that always points inward. In an orbit, the inward acceleration is always present. The sideways motion is always present. The path is the compromise. The 5th unlock rests on a common confusion. Speed is not what makes an orbit stable by itself. Stability comes from the match between speed and the field at that distance. Too slow and the path falls inward. Too fast and the path stretches into a long oval or escapes. That match appears as a just right lane in the disk. Now a limit of intuition arrives softly with a clear boundary. Intuition expects a neat curve that can be drawn once and trusted forever. Reality resists that simplicity. No measurement of distance and speed is perfectly exact. A signal would blur slightly as it crosses gas and dust. Even with precise tracking, the smallest uncertainties remain. Over long spans, those uncertainties can grow in predictions. In many body motion, tiny differences can change the timing of close approaches. The limitation is in long-term forecasting. The present orbit can be known well, the far future orbit can be uncertain in detail. Yet the sixth unlock follows from that limitation. Uncertainty in detail does not erase stability and structure. Stable regions still appear as bands and gaps. Their existence is robust even when exact phases cannot be pinned for eons. Another visual anchor returns to the disk, but with a new focus. Light grazes the surface of the dust plane. The top layer glows. The mid-plane stays darker. Thin ripples appear as faint arcs. The ripples hint at waves of density moving through the disk. Gravity drives those waves. The waves do not speak. They simply travel where the field allows. The seventh unlock sits in the ripples. Gravity can organize matter without any contact by shaping how paths intersect and how often. When intersections are gentle, matter remains spread. When intersections are frequent, matter collides and settles into thinner lanes. The final transition softens toward what comes next. The next step is to name the partner that keeps gravity from becoming collapse. The sideways stored turning becomes the quiet counterweight, and the path's changing speed begins to make sense. A stable orbit reveals itself most clearly when speed changes without breaking the pattern. Angular momentum keeps the sideways sweep consistent, so the path tightens and loosens without collapsing. In that region, a slow visual settles on a stretched ellipse traced in dust. The ellipse has a narrow end and a wide end. The dust lane looks denser near the narrow end. It looks thinner along the wide arc. The first unlock appears in that uneven density. Speed is not constant along an orbit. Speed trades with distance in a steady way. Near the central mass motion becomes faster. Far away it becomes slower. The trade is guided by conserved turning. A new term enters gently. Angular momentum is the amount of turning carried by motion. The phrase stays short. The idea returns to imagery. A figure skater spins faster when arms draw inward. The spin slows when the arms open outward. The importance lands quietly. Orbits behave in a related way. When distance shrinks, turning concentrates and speed rises. When distance grows, turning spreads and speed falls. A second visual anchor appears closer to the path itself. A comet-like body passes through a faint halo of dust. The dust forms a thin wake. The wake curves. The curve is smooth. The wake is brightest near the closest pass. It fades into a softer arc farther out. That brightness change is a physical detail tied to motion. Near the closest pass, the body moves faster and sweeps more dust per time. Far out, it moves slower, and the wake becomes subtle. The second unlock follows. A closed orbit is not held together by equal speed. It is held together by equal rules. The rules connect the fast segment and the slow segment into one loop. A single number anchors the feel of the change without heavy math. In a typical inner orbit, speed near closest approach can be about twice the speed far away, like a river that narrows and quickens at a pinch point. The analogy stays every day. It keeps the ratio tangible without equations. The scale shift arrives next. The change happens over months and years for some worlds. The same pattern unfolds over centuries in the outer system. The tempo stretches, but the trade remains. Another scene opens in a band of small bodies. Some paths are nearly circular. Some are long ovals that cross wide regions. The ovals have a line of closest points that slowly drifts. The drift is gentle. It is not a sudden swing. The third unlock rests there. Even when an orbit changes orientation, angular momentum still constrains how the body moves along it. The orbit can rotate in space and remain stable. The change is like a slow turn of a drawn shape on paper. The shape stays the same. The direction it points shifts. A fresh analogy supports the idea without repeating earlier ones. A loop of thread pulled through fingers keeps its length. The loop slides. The curve changes position, but the thread does not vanish. In space, the thread is the constraint of turning. It keeps motion from falling straight inward. A new visual anchor arrives with a clear boundary. A planet is seen as a dark disk against scattered light. A thin atmosphere glows at the edge. The edge forms a narrow ring of brightness. A small moon crosses that ring and casts a shallow shadow. The shadow slides across the atmosphere. The sliding shadow marks changing speed. It moves faster near the point of closest approach. It moves slower when the moon is farther along the arc. The fourth unlock appears in the shadow's pace. Speed changes can be inferred from geometry. The orbit's shape and timing reveal the conserved turning. Yet intuition can mislead. It expects the inward pull to steal speed until motion stops. It expects friction that is not there. In space, the inward pull redirects motion rather than draining it. The speed rises as the body falls inward because potential becomes kinetic. The speed falls outward because kinetic becomes potential. The exchange is reversible in the ideal case. The fifth unlock lands there. An orbit is a continuous conversion between height in the field and speed along the path. The conversion is gentle. It is also strict. Now a limit of observation enters softly with a clear statement of what fails. The smallest changes in speed along an orbit are hard to measure directly at great distance. Light behaves as a finite messenger. It carries timing and colour shifts, but those shifts can be blurred by noise and by intervening dust. When many bodies tug at once, models must estimate unseen masses and their positions. Over long prediction windows, tiny errors in initial speed can grow into large uncertainties in where a body will be. The limitation is not only instrument sensitivity, it is also the compounding nature of orbital dynamics. Yet the sixth unlock follows from the limit. Even with imperfect detail, the signature of angular momentum is robust. Orbits that remain bound still show faster motion near the centre and slower motion far away. The pattern appears again and again across the system. Another slow scene returns to the dust disk, but with a new focus. Particles drift into a narrow lane. The lane has a sharp inner rim and a softer outer fade. The sharp rim is a boundary where higher speeds shear the material. The shear prevents clumping. It keeps the lane thin. The seventh unlock sits in that shearing. Conserved turning does not merely keep an object from falling. It also shapes how material spreads into rings and gaps. Faster inner motion stretches structures. Slower outer motion allows thicker bands to persist. A final scale shift broadens the view. In the inner system, the exchange between speed and distance plays out over seasons of motion. In the outer darkness, it plays out over lifetimes of ice and shadow. Over billions of years, the same conserved turning allows repeated loops to accumulate into stable architectures. The close of the section eases toward the next step. The next idea is timing between bodies. Repetition in timing can strengthen stability or wear it down. Resonance begins as a quiet clockwork of phases and its effects begin to appear. Some orbits look steady because their shape repeats even while their hidden accounting shifts. Orbital energy sets whether a path stays bound or drifts away, and that decision can be read from shape. At this distance, a quiet scene forms around a close pass. A small body skims through a thin veil of dust. The veil is denser near the centre and fades outward. The pass leaves a faint arc behind it, brighter on the inside edge. The first unlock arrives in that brightness. A bound orbit is a path that cannot wander off to infinity. It keeps returning because the total energy stays below the escape threshold. The threshold is not a wall. It is a dividing line between loops and open curves. A new term enters briefly. Orbital energy is motion plus gravity potential in one total. The idea returns to plane images. A ball rolling in a valley can climb partway up a slope. It slows, then returns. The importance lands softly. A bound orbit behaves like that valley path. It can stretch outward and still come back. The next visual anchor shifts to a wider frame. A long ellipse is seen as a dim ribbon in space. One end of the ribbon narrows into a tight bend. The other end spreads into a broad arc. The ribbon's curvature changes smoothly. Near the tight bend, the curve is sharp. Far out, the curve is gentle. That physical change is the second unlock. The sharper the bend near the centre, the more the orbit is held by gravity. A nearly straight segment far away hints at a path closer to escape. Shape reveals energy without needing constant speed. Another analogy supports the idea without repeating earlier ones. A stone skipped across ice can either settle into a wide circle or drift off the edge. The same initial push set at a different angle changes whether the motion stays in the rink. In space, the rink is not solid. It is the gravitational well. A single safe number anchors intuition. Escape speed from a temperate world is about 11 kilometers per second, like crossing a city in the time of a short song. The comparison keeps scale gentle. The scale shift follows. That speed is a brief flash near a planet. In the solar system as a whole, the decision between bound and unbound plays out over years and centuries. A small change at one close pass can echo over many returns. Another scene arrives with clear boundaries. A planet's gravity well is imagined as layered contours. The contours are closer together near the planet. They spread out with distance. A passing body cuts across the contours. The path bends more where contours crowd. It bends less where contours spread. The third unlock sits in the contour spacing. Gravity's change with distance is what makes energy matter. Closer in, a small change in speed can change the path a lot. Far out, the same change shifts the orbit more gently. This prepares a quiet checkpoint. Close approaches are the places where stability is tested. A close pass can trade energy between bodies. It can stretch an ellipse or round it. It can move the closest point inward or outward. Yet most close passes never happen. Most orbits remain separated by distance and timing. The fourth unlock follows. Stability often comes from not meeting. Orbits can be safe because geometry keeps bodies apart even as they share the same central pull. A new visual anchor forms in a narrow belt. Countless small bodies circle in a band. Within the band, faint gaps appear as dark lanes. The edges of the gaps are sharp. The sharp edges indicate long sorting. Some orbits are removed because they cross too often. Some remain because they do not. Energy and shape decide which lanes survive. Now the section touches a limit of intuition and observation stated clearly. The energy of an orbit is not measured directly. It is inferred from position and motion over time. At great distances, the motion is small on the sky. The signal would be faint. Dust and glare can blur the track. Models must estimate unseen influences. Even small uncertainties in distance can change the inferred energy. Over long spans, that uncertainty grows. The limitation is in reconstructing the exact past and exact future. Yet the fifth unlock follows from that limitation. The bound or unbound distinction remains reliable because shape is forgiving. A clearly closed ellipse is bound. A clearly open hyperbola is unbound. Many real cases sit between, but the broad categories still guide understanding. Another gentle scene returns to the passing body near a planet. The body approaches on a steep arc. It swings around and leaves on a new direction. The curve is smooth. The closest distance is not a collision. A narrow, safe gap remains. The gap is a physical boundary. It separates a stable flyby from a disruptive encounter. The sixth unlock rests there. Stability is not only about staying bound to the sun, it is also about avoiding energy exchanges that reshape the orbit too strongly. Most of the solar system's long-lived objects inhabit corridors where close passes are rare. A slow scale shift expands outward again. In the inner system, close passes and energy changes can matter over millions of years. In the outer system, the same story stretches over billions of years. The field is weaker, but time is longer. Small changes have longer to accumulate. The section eases toward the next mechanism that decides how changes accumulate. Timing between orbits begins to matter more than single encounters. Repeated alignments can add gentle nudges into something lasting, and the first quiet doorway into resonance begins to open. A steady solar system is built from repeating timings as much as repeating shapes. Resonance appears when orbital periods fall into simple ratios and small tugs align again and again. In that region, a slow visual forms around two moons circling the same planet. One moon moves on an inner track, the other moves on a wider track. Their paths are thin rings of motion. Each ring has a crisp inner edge and a softer outer haze. Every so often the moons line up. The lineup repeats with a calm regularity. The first unlock arrives in that repetition. A tug does not need to be strong to matter. It needs to arrive at the same phase. Resonance is phase memory. It turns gentle nudges into a pattern. A new term enters briefly. Resonance is repeated gravitational kicks at the same timing. The phrase stays short. The idea returns to plain images. A swing rises higher when pushes match its rhythm. A push at the wrong moment does little. The importance lands softly. In orbits, timing can build stability or wear it down. The next visual anchor moves outward to a belt of small bodies. The belt looks like a dusty band. It carries dark lanes that cut through it like clean seams. The seams have sharp boundaries. Those boundaries are physical evidence of sorting. Some paths are emptied because repeated timing removes objects from those lanes. Some paths remain because timing protects them. The second unlock follows. Resonance can clear gaps, and it can also lock bodies into safe choreography. The same mechanism can sculpt order and absence. A single safe number anchors the idea without heavy notation. A 3-to-2 resonance means one orbit completes 3 loops, while the other completes 2 like 2 metronomes that meet on the same beat every few ticks. The comparison stays gentle. It makes the ratio feel like a shared rhythm rather than a calculation. The scale shift comes next. Those meetings can occur over days for close moons. The same kind of phase alignment can stretch over centuries for distant objects. The tempo changes. The cumulative effect remains. Another scene forms in a ring system. A narrow wave travels through the ring as a bright spiral stripe. The stripe is slightly denser than the surrounding material. Its leading edge is sharp, its trailing edge is softer. The stripe marks where repeated tugs compress particles. The third unlock rests inside that spiral stripe. Resonance does not require contact. It can create structure through repeated timing alone. Compression and rarefaction travel like quiet weather through the ring. Now the section deepens into the mechanics with controlled steps. Inner resonance conjunctions occur at similar longitudes again and again. The tug points along a consistent direction. That direction can pump up eccentricity, stretching an orbit into a longer oval, or it can keep eccentricity small by alternating pushes that cancel. The outcome depends on phase. The fourth unlock appears there. Resonance is not only a ratio, it is a relationship of angles. Two bodies can share the same ratio and still behave differently depending on where the alignments happen along the orbit. A fresh analogy supports the angle idea without repeating earlier ones. Two ripples on a pond can add into a taller wave if crests meet. They can flatten if a crest meets a trough. The timing is the same. The phase decides the effect. In space, the wave is the orbit's shape. The meeting is the repeated alignment. A new visual anchor appears near a planet's shadow. A small moon crosses a faint atmospheric glow. The shadow line on the planet is smooth and curved. Over many orbits, the crossing points drift slowly. In resonance, that drift can pause. The crossings occur near the same parts of the shadow line, leaving a repeated pattern in where shadows fall. The fifth unlock sits in that repeat. Resonance can stabilize by keeping close approaches away from danger. It can place encounters where distance stays safe. Or it can destabilize by bringing close approaches into the same corridor each time. This leads into a limit of observation stated clearly. Resonance is often inferred, not directly watched, through every cycle. At great distance, a signal would carry only a small change in position against a crowded background. The timing must be pieced together from sparse measurements. Noise and faintness blur the exact phase. Models must assume masses and unseen companions. Over long spans, small phase errors accumulate. The limitation is uncertainty about the exact resonant angle. Yet the sixth unlock follows. Even when phase cannot be pinned, precisely resonant structure leaves durable signatures. Gaps remain. Clusters remain. Narrow bands of stability stand out. The system advertises its resonances through what survives. Another slow scene returns to the belt with dark lanes. Along the edges of one lane the density rises. It looks like a shoreline of dust. Tiny particles gather in a narrow ridge. That ridge is a boundary where stable paths pile up after unstable ones are removed. The seventh unlock arrives in that ridge. Resonance can act like a sieve. It lets certain timings pass and rejects others. Over time, the belt becomes organized not by design but by repeated selection. A gentle scale shift broadens the view again. Over thousands of years, a resonance can move an object from one lane to another by slowly pumping its orbit. Over billions of years, whole regions can be reshaped as planets drift slightly, and resonances sweep across space. The changes are slow. They're also persistent. The section eases toward the next step without opening a new mystery. The next layers add many small tugs at once. Perturbations begin to stack, and the line between smooth change and sensitive change begins to show. A quiet orbit can stay steady even while countless small pulls brush past it. Perturbations are the small gravitational nudges from other bodies, and most of them average into slow drift rather than sudden change. At this distance, a slow visual forms in a broad asteroid belt. The belt looks like a faint band of grit. Within it, thin lanes appear slightly brighter. Between lanes, darker corridors open. Along one corridor, the edge is crisp like a clean cut. Along the other edge, the dust fades in a soft gradient. The first unlock sits at that boundary. Small tugs do not act alone. They stack in time. When their directions vary, their effects tend to cancel. What remains is a gentle, predictable drift. The scene moves inward. A planet carries a pale halo of dust near its orbit. The halo is not uniform. It shows faint arcs and clumps. The arcs are stretched into long curves. The clumps smear out into streaks. Those streaks are physical traces of shearing. The second unlock follows. Perturbations often show up as slow reshaping rather than fast scattering. A shape can remain bound while its ellipse slowly rotates. A tilt can change while distance stays similar. A new term enters briefly. A perturbation is a small extra force beyond the main pull. The idea returns to plain imagery. A boat in a wide current keeps moving forward. Tiny side eddies push it left and right. The path wobbles slightly but does not reverse. The importance lands softly. In the solar system, the main current is the sun's gravity. The eddies are other planets and moons. Their pushes are real but usually not synchronized. Another visual anchor settles on an orbit plane. A thin sheet of motion tilts slightly relative to a second sheet. Where the sheets intersect, a line forms. Along that line, crossings repeat. The line slowly turns like a seam rotating in cloth. The third unlock rests there. Some changes are not about distance, they are about orientation. A path can be stable in size and still drift in where it points. This prepares a key checkpoint. The averaging of perturbations depends on timescale. On short times, a nudge is just a nudge. On long times, the same nudge can accumulate if it repeats with the right rhythm. If it does not repeat, it becomes background. A single safe number anchors the feel of slow accumulation. A tiny change of about 1 degree in an orbit's orientation can take thousands of years to unfold, like a slow hand turning on a deep ocean current. The comparison stays gentle and natural. The scale shift follows. Thousands of years is long compared to one orbit. It is short compared to the age of the system. Over billions of years, many such slow turns can occur. The system can reshape without breaking. Another scene arrives near a planet's shadow. A ring system is seen edge-on. The ring becomes a thin line. Along the line, brightness varies. Narrow bands appear as bright threads. Dark gaps cut between them. A moon passes nearby. Its gravity raises a slight wave in the ring. The wave travels as a kink that keeps its shape for many orbits. The fourth unlock appears in that travelling kink. A small perturber can imprint a pattern that persists. The pattern is not the moon's choice. It is the ring's response to repeated timing. This leads gently into the deeper mechanism of secular change. Secular effects are long-term averages that ignore short wiggles. The word is defined briefly. Secular means long-term average change over many orbits. The idea returns to plain language. Short-term pushes come and go. The average push sets the slow direction of drift. The importance lands softly. Secular drift explains why many orbits stay stable while still changing slowly. Another analogy supports the averaging without repeating earlier images. A candle flame in calm air leans one way under a steady faint draft. Random swirls make it flicker. The lean remains because it is the average. In the solar system, the lean is the slow rotation of an orbital ellipse or the slow change of inclination. Now, a limit of observation enters with clear boundaries. Secular drift is difficult to confirm directly over short monitoring windows. The changes can be smaller than measurement precision at great distance. Light behaves as a finite messenger. It carries position, but the position can be blurred by dust and glare. Models must infer tiny precessions from sparse snapshots. When several planets contribute, the contributions overlap. The limitation is in separating causes. A slow drift can look like noise unless it is tracked over long time spans. Yet the fifth unlock follows. Even when the drift cannot be watched in real time, its results can be read in structure. Rings show wave patterns, belts show clustered families. Stable inclinations appear as preferred layers. The system stores its secular history in how populations arrange themselves. Another visual anchor settles on a set of nearly parallel rings. Between two rings, a faint haze fills the gap. The haze is not uniform. It forms a thin, rippled sheet. The ripples are tightly spaced on the inner side and more spread on the outer side. That spacing is a physical detail tied to orbital speed differences. Faster inner motion stretches patterns. Slower outer motion lets them thicken. The sixth unlock rests there. Perturbations interact with shear. Shear is the speed difference across distance. Shear can smear disturbances into smooth arcs, making the system more stable by distributing energy. The story deepens with a controlled escalation. When perturbations align with an orbit's rhythm, resonance appears. When they do not, they become secular drift. Many regions are ruled by drift and remain calm. Some regions sit near resonant seams and become sensitive. The line between the two can be narrow. That narrowness is part of what makes the solar system both ordered and intricate. A final scale shift broadens the view again. In the inner system, perturbations can rearrange small bodies over millions of years. In the outer system, the same gentle nudging can work over billions. The closings soften toward the next section. The next step moves from average drift into sensitive dependence. In some resonant neighborhoods, small differences can grow until prediction becomes uncertain and the first quiet shape of chaos begins to appear. Some regions of space look calm until tiny differences begin to separate very slowly at first. Chaos in orbital motion is sensitivity to initial conditions where small uncertainties grow into large prediction gaps. At this distance, a slow visual forms in a narrow corridor between resonant lanes. Two small bodies travel on nearly identical ellipses. The ellipses overlap like two faint pencil loops. Their closest points sit almost together. Their far arcs nearly touch. The loops have a thin inner edge and a soft outer blur. The first unlock sits in that closeness. Chaos does not require violent motion. It can arise in gentle curves when timing and tugging interact. The motion stays bound. The future becomes hard to pin. A new term enters briefly. Chaotic means tiny differences grow rapidly in time. The phrase stays short. The idea returns to imagery. Two drops of dye released side by side can drift apart in a swirling stream. The water remains calm on the surface. The hidden swirls separate the colours. The importance lands softly. In orbital chaos, the hidden swirls are overlapping resonances and repeated perturbations. They can stretch and fold the space of possible paths. The scene shifts to a belt with thin gaps. The gaps are not smooth. Their edges look jagged in density. Small clusters appear then thin out. The density rises along one boundary like a shoreline of grit. The second unlock follows. Jagged edges often signal sensitive dynamics. Stable regions fill in smoothly. Chaotic regions show ragged borders where objects leak away over time. Another slow visual anchor arrives near a planet and a small moon. The moon's orbit is slightly tilted. The tilt creates a thin shadow track on a faint atmospheric glow. The shadow track does not repeat exactly. It drifts. Sometimes it drifts smoothly. Sometimes it jumps to a nearby band. That physical jump is subtle. It is a boundary crossing in phase space, not a collision. The third unlock rests there. Chaos can appear as sudden switches between nearby patterns, even when forces change smoothly. The switch happens when a path wanders near a separatrix, a dividing curve between modes of motion. The term is introduced briefly. A separatrix is a boundary between different repeating behaviours. Two sentences of imagery carry it. A ridge on a hillside divides where rainwater flows. A drop on one side goes to one valley. A drop on the other side goes elsewhere. The importance lands gently. In orbital dynamics, being near that ridge means small changes decide which long-term pattern applies. A single safe number anchors the feel of separation. Two paths that begin only 1 kilometre apart can diverge until their positions differ by millions of kilometres, like two threads that start together and end on opposite sides of a wide fabric. The comparison stays every day. It carries scale without formulas. The scale shift follows. A kilometre is a small span near a planet. Millions of kilometres is a gulf in interplanetary space. The growth can take thousands or millions of years. It can also happen faster in strongly perturbed zones. Another checkpoint arrives with a calm clarification. Chaos does not mean randomness in the laws. The laws remain deterministic. Chaos means practical unpredictability when initial conditions are not known perfectly. The fourth unlock sits in that distinction. A chaotic orbit can be stable in the sense of remaining bound for long times. It can still be unstable in predictability. It may wander among allowable shapes without escaping. The scene returns to the two overlapping loops. Over many orbits, their closest points drift apart. One loop becomes slightly rounder, the other becomes slightly more stretched. Their planes tilt by tiny amounts. The changes are small each cycle. The accumulation is large. A new analogy supports the accumulation without repeating earlier ones. A folded paper fan opens from nearly the same hinge. Each fold is small. The overall spread becomes wide. In chaos, repeated small stretches and folds of phase space create large separations. Now, a limit of observation enters softly with clear boundaries. Long-term chaos is difficult to confirm by direct tracking over the full timescale. Observations cover short windows compared to the divergence time. At great distance, a signal would be faint. Position measurements have finite precision. Small errors in distance and velocity remain. Models add uncertainty because not every small body is tracked. Not every mass distribution is known exactly. The limitation is not only measurement noise. It is also incomplete information about all perturbers. Yet the fifth unlock follows. Chaos still leaves measurable footprints. It creates diffusion in orbital elements. It creates depleted zones where orbits wander into resonant loss channels. It creates families with spread that is broader than simple collisions would produce. Another slow visual anchor settles on a resonance web. Several narrow resonant lines cross a region of space. The lines are not drawn, but implied by where dust gathers and where gaps open. The crossings form a lattice of influence. At the crossings, behaviour changes more quickly. The sixth unlock rests there. Overlapping resonances are a common doorway into chaos. A single resonance can confine motion. Many resonances together can create a maze of weak pathways. Objects can drift through that maze slowly like mist seeping through a field of reeds. The final scale shift broadens outward. In the inner system, chaos can reshape small body populations over millions of years. In the outer system, it can work over billions because time is abundant even when forces are weak. The section softens toward what comes next. The next step is to identify where stability is strongest. Some regions behave like quiet basins with wide margins. Those basins begin to appear as safe neighbourhoods in the architecture of the solar system. Stability becomes easiest to see where motion has room to breathe and few rhythms collide. Safe neighbourhoods in the solar system are regions where perturbations stay weak or cancel, so orbits remain bounded for very long spans. At this distance, a slow visual forms in the asteroid belt again, but the focus shifts. A broad band shows patches of higher density. Between patches, corridors remain surprisingly empty. The empty corridors have edges that are clean and sharp. The sharpness is a physical boundary. It suggests that long sorting has been at work. The first unlock rests at that edge. A safe region is not defined by calmness alone. It is defined by margins. Small changes do not immediately push an orbit into a dangerous crossing. The scene moves inward to a quieter band. Several small bodies share similar inclinations. Their orbital planes form a thin layer like a sheet of drifting ash. The sheet is not perfectly flat. It has a gentle warp. The warp is a gradient in tilt across distance. The second unlock follows. Layers form when certain inclinations avoid repeated kicks. The system becomes stratified. Some layers persist because the main resonances miss them. A new term enters briefly. A stability zone is a region where orbits resist large changes. The idea returns to plain imagery. A calm bay can hold floating debris without sending it into open surf. The bay still has waves. The boundary shelters it from the strongest currents. The importance lands softly. In orbital space, boundaries are created by resonance lines and by the reach of planetary tugs. The next visual anchor settles near a planet's orbit. Two faint streams of dust run ahead of and behind a planet along the same path. The streams are not continuous rings. They look like tapered clouds. Their leading edges are sharper. Their trailing edges fade. The planet itself remains a distant point. The dust clouds mark stable co-orbital regions where motion can linger without collision. The third unlock appears in that lingering. Stability can come from sharing an orbit in a balanced geometry, not only from being far away. A gentle analogy supports the balance without repeating earlier ones. Leaves can gather in two eddies on either side of a rock in a stream. The flow continues. The leaves remain trapped in the eddies because the local currents balance. In space, the rock is the moving gravitational pattern of a planet. The eddies are stable regions that travel with it. A single safe number anchors how close stability can be. A region can remain stable for about 1 million years, like a shoreline that holds its shape through many seasons of tide. The comparison keeps the span tangible without human calendars. The scale shift follows. 1 million years is long compared to any single orbit. It is still short compared to the age of the solar system. Some neighbourhoods remain stable for billions of years. Others last only until slow drift moves them across a boundary. Another scene arrives with a clear physical detail. A belt of debris shows a narrow gap. The gap is not completely empty. It holds a faint haze of dust. The haze is grainy and uneven. It forms small clumps that stretch into arcs. Those arcs show that some objects pass through but do not stay. The fourth unlock rests in that faint haze. A gap can be a corridor rather than a void. It can be traversed but not inhabited. A safe neighbourhood is the opposite. It is inhabited. It shows a steady population because objects do not get steadily removed. The section deepens into controlled mechanisms. Distance from major planets matters. inclination matters, eccentricity matters. Yet the core idea stays calm. Stability comes from avoiding repeated close alignments that add rather than cancel. It comes from being in regions where resonant angles circulate harmlessly instead of locking into a kick. Another visual anchor settles on a set of nested orbital shells around the Sun. Each shell is imagined as a thin, translucent ring. Some rings are smooth, some have ripples. The ripples concentrate near certain radii. The smooth rings sit between rippled ones. The fifth unlock appears in that contrast. Smooth zones are often the stable neighbourhoods. Ripples mark places where resonances or strong perturbations disturb the flow. This leads into a limit of observation stated clearly. Safe neighbourhoods are not labelled directly by any single measurement. They are inferred from populations and long-term integrations. Observations show where bodies are now. They do not prove where bodies can remain for billions of years. A signal would be limited by faintness and by background confusion. Small bodies are numerous and dim. Many remain undiscovered. Models that map stability must assume distributions and approximate influences. The limitation is incomplete sampling and finite computation time. Yet the sixth unlock follows. Even with incomplete knowledge, the architecture is visible in broad strokes. Gaps persist at resonances. Families cluster in stable lanes. Co-orbital clouds remain in balanced regions. The system repeatedly points to the same safe neighbourhoods through structure. Another gentle scene returns to the layered sheet of inclinations. The sheet meets another sheet at a shallow angle. Along the intersection, a faint line of nodes forms. The nodes drift. The drift is smooth, not jerky. The smoothness suggests that perturbations are being averaged rather than amplified. The seventh unlock rests there. Stability often appears as smooth precession rather than erratic wandering. The orbit changes its orientation like a slow-turning leaf, while keeping its size and shape within bounds. A final scale shift broadens the perspective. Over centuries and millennia, safe neighbourhoods look almost static. Over millions of years, they reveal slow migration as planets and belts exchange angular momentum. Over billions of years, they define what the solar system retains. The close of the section eases forward. The next step looks at patterns that hold two bodies in shared motion more explicitly. Co-orbital balance points begin to sharpen into distinct regions, and stable companionship without collision becomes clearer. Some stability looks like companionship, where two paths share a rhythm without ever meeting. Lagrange regions are balance points in a moving gravitational landscape, allowing co-orbital motion to persist. At this distance, a slow visual forms along a planet's orbit. Two tapered clouds of dust hover ahead of and behind the planet. Each cloud has a sharper leading edge and a softer trailing fade. The clouds sit like gentle commas on the orbit. They remain in place relative to the planet while everything moves around the Sun. The first unlock rests inside that stillness. Stability can exist in a frame that moves. A co-orbital object can share the planet's average distance from the Sun and still avoid collision. It does so by staying in a protected geometry. A new term enters briefly. A Lagrange point is where forces balance in a rotating frame. The phrase stays short. The idea returns to imagery. A bead can rest in a shallow notch on a spinning ring. The ring turns, yet the bead stays near the notch because the local slopes guide it back. The importance lands softly. In orbital space, the notch is not a physical groove. It is a contour in the combined gravity of Sun and planet plus the effect of rotation. The scene deepens into the moving landscape. Around the planet's orbit, the gravitational contours bend. Some contours form pockets. In a pocket, a small object can drift and still remain nearby. It traces a looping path that does not close tightly. It librates, swinging gently around a balance region. The second unlock follows. Co-orbital stability is often a slow oscillation, not a fixed point. The object does not sit motionless. It moves in a wide, calm figure around the pocket's centre. Another visual anchor appears at the edge of a dusty cloud. Individual grains cross the boundary and then return. The boundary is visible as a change in density. Inside, grains appear more concentrated. Outside, the haze thins. The boundary behaves like a shoreline in phase space. The third unlock rests there. A stable region can have a soft edge. Objects can wander near that edge and still be guided back as long as energy stays within the pocket. A gentle analogy supports the guidance without repeating earlier ones. A marble rolling inside a shallow saucer can circle near the rim and still fall back inward. The saucer is not deep. The marble is not trapped forever if a strong shake arrives. Yet gentle motion remains bounded. In the solar system, the shake is strong resonance, overlap, or a close encounter. In quiet times, the pocket holds. A single, safe number anchors the geometry. The leading and trailing pockets sit about 60 degrees ahead, and behind the planet like the corners of a wide triangle cut from a circle. The comparison keeps angle simple and spoken cleanly. The scale shift follows. Near a planet, the distance across these pockets can be millions of kilometers. At the same time, the structure is defined by an angle rather than a fixed length. It scales with the orbit itself. Over thousands of years, objects can drift within the pocket. Over billions of years, the pocket can remain recognizable if the planet's orbit stays stable. Another scene arrives with a precise physical detail. The dust cloud shows faint streaks inside it. The streaks curve like elongated arcs. Their curvature changes across the cloud. Near the inner side, streaks are tighter. Near the outer side, streaks are broader. That gradient is shear at work. The fourth unlock appears in the streaks. Co-orbital regions are shaped by both balance and shear. Shear stretches the cloud. Balance keeps it from dispersing completely. Together they create a persistent, sculpted swarm. The section moves into a calm checkpoint. Not all co-orbital motion is the same. Some objects stay near the leading pocket. Some stay near the trailing pocket. Others take wide horseshoe paths that loop around both pockets, avoiding the planet by trading distance slightly inward and outward. The fifth unlock rests there. Avoidance can be built into geometry. A horseshoe path is stable because the closest approach is prevented by the timing of the oscillation. The object turns away before crossing the planet's position. It is guided by the same contours that define the pockets. Now a limit of observation enters softly and clearly. Co-orbital objects can be hard to detect because they share the planet's path. Against the background, their apparent motion can be slow. A signal would be faint. Dust and glare near a planet's orbit can hide small bodies. Measurements of their libration require long monitoring windows. Models must infer stability from partial arcs, not from complete cycles. The limitation is incomplete sampling of the full oscillation. Yet the sixth unlock follows. Even with partial data, co-orbital structure can be recognized by clustering. Objects gather near expected angles. Dust swarms appear where balance should exist. The pattern repeats across different systems and scales because the underlying geometry is general. Another visual anchor settles on the rotating contour map again. The contours form a saddle shape near one balance point. Along the saddle motion is unstable. Across it motion can be stable. The saddle's ridge is a thin dividing line. The seventh unlock rests on that ridge. Stability near Lagrange regions depends on staying in the right side of a saddle. Small changes can move an object from trapped oscillation to slow escape. The boundary is subtle. It is not a dramatic threshold. A final scale shift broadens outward. Co-orbital pockets are local features. They sit inside the larger architecture set by resonances, perturbations, and chaos. A pocket can survive for immense time if larger scale conditions remain gentle. The section eases toward what comes next. The next step is to introduce a slow drain of energy that changes orbits without explosions. Tidal dissipation begins as faint flexing and gradual circularization, and it quietly reshapes long-term stability. A long-lived orbit can change without any sudden shove simply by leaking a little motion into heat. Tides and dissipation slowly remove energy from a system rounding orbits and locking rhythms over immense time. At this distance, a slow visual forms around a moon circling close to a planet. The moon is not perfectly round. It shows a subtle bulge that points slightly away from the planet's centre line. The bulge is small but persistent. Along the moon's surface, the bulge creates a gentle gradient in elevation. The gradient shifts as the moon moves. The first unlock rests in that shifting shape. Gravity can deform a body. Deformation can waste energy. That wasted energy must come from orbital motion, or spin. The motion becomes a little less free each cycle. A new term enters briefly. Tidal dissipation is orbital energy turning into internal heat. The phrase stays short. The idea returns to imagery. A rubber ball squeezed and released warms slightly with each squeeze. The ball does not explode. It simply loses a little motion to warmth. The importance lands softly. In orbital systems, repeated flexing plays the role of the squeeze. A moon flexes more when its orbit is stretched. Flexing tends to reduce that stretch over time. The next visual anchor shifts to the orbit's shape itself. The moon's path is an ellipse. The ellipse is not extreme, but it is not a perfect circle. Near closest approach, the moon moves faster. Farther out it slows. Each pass changes the tidal force. The force is stronger at the close end. It is weaker at the far end. That variation drives the flexing cycle. The second unlock follows. Tides prefer uniformity. They tend to circularize an orbit because a circle keeps the tidal forcing more constant. The scene deepens with a quiet checkpoint. Circularization is slow. It depends on the material inside the body. A rigid, cold body dissipates less. A warm, deformable body dissipates more. The orbital energy lost per cycle is tiny, but it repeats countless times. A single safe number anchors the scale. A close moon can orbit in about 1 day like a slow, steady drumbeat that repeats without pause. The comparison keeps rhythm tangible. The scale shift follows. A day is brief compared to the time needed for tides to reshape an orbit. Circularization can take millions or billions of years. The same small flex repeats so many times that it becomes decisive. Another visual anchor appears near the planet's limb. The planet shows faint banding in its atmosphere. A dark shadow from the moon slides across those bands. The shadow's speed is steady. The shadow returns at nearly the same longitude each cycle. Over long time, the return becomes exact. This introduces the next mechanism without jargon overload. Spin and orbit can synchronize. The moon's rotation can slow until the same face points toward the planet. The third unlock rests in the shadow's repeating track. Tides can lock a rhythm. Locking reduces ongoing flexing in some cases because the relative motion becomes simpler. Yet locking does not end all dissipation. If the orbit remains slightly eccentric, flexing continues. If the planet rotates faster than the moon, orbit's tides can transfer angular momentum and shift the orbit outward. The section holds to 2 core concepts. Dissipation converts energy. Angular momentum exchange can move orbits. Both happen quietly. A fresh analogy supports outward drift without repeating earlier ones. A spinning carousel can hand some of its motion to a loosely held bead near the rim, causing the bead to drift outward as it gains angular momentum. The bead remains on the carousel, but its radius changes. In orbital terms, a moon can drift outward while staying bound. The fourth unlock appears here. Energy loss does not always mean inward fall. The direction of orbital migration depends on where angular momentum comes from and where it goes. Now the limit of observation enters softly with clear boundaries. Tidal dissipation is hard to measure directly because it is slow and subtle. The heat produced can be small compared to other sources. The orbital changes per year can be below detection for distant systems. A signal would be limited by faintness and by the blending of light from multiple components. Models must infer dissipation from present-day shapes and resonances. They must assume internal structure that cannot be seen directly. The limitation is in hidden interiors and in long timescales. Yet the fifth unlock follows. Even with those limits, tides leave recognizable fingerprints. Orbits close to planets tend to be rounder than simple formation would suggest. Spin states tend to be synchronized. Resonant chains can be stabilized by the gentle damping of eccentricity. Another slow scene returns to the slightly bulged moon. The bulge is not aligned perfectly with the line to the planet. It lags. That lag is the physical detail that makes dissipation possible. If the bulge pointed exactly along the line, the energy would slosh back and forth with less loss. The lag creates torque. Torque changes spin. Torque exchanges angular momentum. The sixth unlock rests in the lag. Dissipation requires delay. Delay is created by friction and viscosity inside the body. The system's long-term evolution is written into that tiny phase offset. A scale shift expands outward again. Near a planet, tides can dominate orbital shaping. Far from planets, tides weaken, and perturbations dominate instead. The system has different sculptors in different zones. In the inner, close-in neighbourhoods, tides smooth and lock. In the wider neighbourhoods, resonances carve and perturbations drift. The closing of the section eases forward. The next step moves from individual systems to chains and consequences. When tides damp some motions, resonances can hold others more firmly. The broader architecture begins to show how slow losses and repeated timings cooperate to preserve stability across vast time. When many orbits coexist, stability becomes a collective pattern rather than a single path. Resonant chains and secular architecture distribute risk, so the system stays ordered even while parts drift. At this distance, a slow visual forms across several neighbouring orbits. 3 worlds circle the same star at different radii. Their orbital planes lie close together like stacked sheets of dark glass. The sheets are not perfectly aligned. A subtle gradient in tilt appears from inner to outer. Along each sheet, faint arcs of dust trace the paths. The first unlock rests in the layered look. A system can remain stable by spreading its interactions across many gentle links. No single pair must carry all the tension. Resonant chains act like shared timing agreements. They keep close approaches out of phase. A new term enters briefly. A resonant chain is multiple bodies linked by period ratios. The phrase stays short. The idea returns to imagery. A set of gears can turn smoothly when tooth counts match. The teeth never collide because their timing is coordinated. In orbits, there are no teeth. The coordination is phase. The importance lands softly. Linked timing can prevent repeated close pulls from stacking in the wrong places. Another visual anchor settles near the middle world's path. A thin band of dust shows faint compression ridges. The ridges appear as bright arcs that drift slowly along the band. The arcs have sharp leading edges and softer trailing fades. The ridges mark where gravitational tugs align in a repeating pattern. The second unlock follows. Resonant chains can store interaction energy as oscillations rather than as chaos. The system breathes in angles and timing. It does not need to break apart. The section moves deeper with controlled steps. When one world runs slightly ahead, another runs slightly behind. Their resonant angles adjust. The adjustments trade small amounts of angular momentum. The trades are gentle. They keep spacing from collapsing. A fresh analogy supports the trade without repeating earlier ones. A line of floating buoys connected by loose elastic can sway with waves. One buoy moves forward and pulls slightly on the next. The line remains spaced because tension spreads along it. In orbital chains, gravity plays the role of elastic. The coupling is weak but persistent. The third unlock rests there. Stability can be an outcome of coupling, not of isolation. A connected system can be more stable than a system of strangers because timing constraints limit dangerous alignments. A single safe number anchors the feeling of coordination. In a simple chain, an outer body can complete one orbit while an inner completes about 2, like 2 slow lanterns circling a pond at synchronized speeds. The comparison stays natural and gentle. The scale shift follows. The synchronization can be tracked over many orbits. Over millions of years, the chain's angles can librate and still remain bounded. Over billions of years, the chain can persist if damping and perturbations stay moderate. Another scene opens to the broader architecture beyond strict resonance. Secular structure appears as slow procession of ellipses and nodes. The ellipses rotate like faint outlines turning in the dark. The nodes drift along a circle of intersections. The drift can be smooth. Several worlds can process together, their ellipses aligned or anti-aligned for long spans. The fourth unlock appears in that alignment. Even without exact resonance, shared precession can reduce close encounters. If closest points line up in a stable way, spacing stays safer. If they drift into certain alignments, risk rises. The system's stability is partly a choreography of slow rotations. A new visual anchor settles on an asteroid belt under the influence of a resonant chain. The belt shows a broad gap. Near the gap edge, the density rises into a ridge. The ridge looks like a dune line of dust. Its crest is sharp, its downwind side is softer. The ridge marks where stable orbits accumulate after unstable ones are cleared. The fifth unlock rests in that ridge. Large-scale architecture shapes small body populations. The chain's gravitational patterns carve where debris can remain. The belt becomes a map of stability corridors and forbidden lanes. Now a limit of observation enters softly with a clear boundary. Resonant chains and secular alignments are difficult to confirm over truly long times. Observations span only a small fraction of the relevant timescales. A signal would be limited by precision in period and phase. Tiny errors in orbital period become large errors in phase after many cycles. Inferring a chain requires assuming masses and mutual inclinations that may not be fully known. The limitation is phase uncertainty over long horizons, yet the sixth unlock follows. The present arrangement can still reveal the architecture. Period ratios close to simple fractions suggest resonance. Correlated precession suggests secular coupling. Population gaps suggest persistent forcing. The system leaves clues that do not require watching every cycle. Another slow scene returns to the stacked orbital sheets. A faint haze lies between the sheets. The haze forms a thin warped layer. The warp is smooth. It suggests that changes are being shared rather than localized. The seventh unlock rests in that smoothness. When the system is stable, changes are often collective and slow. When the system is unstable, changes become localized and fast. The difference can be read in whether patterns look coherent or ragged. A final scale shift widens the view beyond the local neighborhood. A single orbit can be stable for billions of years. A system of many orbits can also be stable for billions when architecture distributes interactions into gentle modes. The section eases toward what comes next. The next step is to consider how architecture can change as planets migrate slightly in the early system. Slow migration can move resonances through space, and the long shadows of that movement begin to appear. Even a stable architecture can be gently rewritten when the largest bodies drift by small amounts. Planetary migration and resonance sweeping shift the locations of stability zones, moving the borders that decide who stays and who leaves. At this distance, a slow visual forms in a broad disk of dust and small bodies. The disk is thin. It has a bright inner rim and a dim outer fade. Within it, narrow lanes appear as faint rings. The rings are not perfectly centered. They show a slight offset like ripples that are being carried downstream. The first unlock rests in that offset. A resonance is not fixed in space. It is tied to orbital periods. If a planet's orbit shifts, the resonance shifts with it. The resonance becomes a moving boundary that can pass through a population. A new term enters briefly. Resonance sweeping is a resonance moving through space over time. The phrase stays short. The idea returns to imagery. A shallow wave in sand can travel across a beach. Grains are lifted and set down as the crest passes. The beach remains, but its patterns move. The importance lands softly. In orbital disks, a sweeping resonance can lift eccentricities and inclinations. It can clear gaps. It can also capture objects into new resonant motion. The next visual anchor settles on a narrow gap inside the disk. The gap is sharp at first. Then it becomes ragged along one edge. Small clumps appear as if debris is piling up. The edge shows a gradient from dense to sparse. The second unlock follows. A moving boundary can create a symmetry. One side is swept clean, the other side gathers what is pushed ahead. The system records motion in the shape of its gaps. The section deepens into controlled mechanisms. Migration can be smooth and slow. It can be driven by exchanges of angular momentum with a surrounding disk of material. It can also be driven by interactions among planets. The details can vary. The core idea remains calm. Small shifts in orbital distance can relocate resonances by large absolute distances because resonances are defined by ratios. A single safe number anchors the feel of small shifts. A change of about 1% in a planet's orbital distance can move a resonance by a much larger span than the planet's own diameter, like sliding a bookmark slightly and shifting the place where many pages open. The comparison stays quiet and familiar. The scale shift follows. 1% is tiny in a local sense. Over millions of years it can reshape entire belts. Over billions of years the new structure can become the stable architecture that remains. Another visual anchor appears near an outer belt. A cloud of small bodies shows a sharp outer edge. The edge is like a cut line in darkness. Beyond it, density drops quickly. Along the edge, streaks point outward. The streaks are elongated arcs. They hint at objects that have been excited into more stretched orbits. The third unlock rests in those streaks. Resonance sweeping can pump eccentricity. Pumped eccentricity increases the chance of crossing other orbits. Crossings increase encounters. Encounters scatter. Over time, the population thins where sweeping has passed. Another analogy supports capture without repeating earlier ones. A leaf caught in a slow whirlpool can circle and drift inward with the rotating flow. It is not forced abruptly. It is carried by a pattern that moves with it. In orbital terms, a body can be captured into resonance if the resonance approaches slowly enough. Once captured, the body's phase stays locked. Its orbit can be transported. The fourth unlock appears here. Slow change can lead to strong constraint. A gradually moving resonance can trap bodies and guide them to new locations while preserving their relative timing. This creates new resonant groups. It also leaves behind empty lanes where non-captured bodies were destabilized. Now a limit of observation enters softly and clearly. Migration and resonance sweeping happen on timescales far beyond direct monitoring. Observations capture the present-day structure. They do not show the moving boundary itself. A signal would be limited by the faintness of distant populations and by the incompleteness of surveys. Models must infer past migration from today's gaps and resonant clustering. They must assume initial conditions that are uncertain. The limitation is in reconstructing history from a single snapshot. Yet the fifth unlock follows. Some signatures are hard to mimic with static processes. Swept resonances leave coherent patterns. They can create sharp edges and broad excitation zones. They can create resonant populations aligned in phase. These patterns act like a fossil record of moving boundaries. Another slow scene returns to the thin disk. A spiral density wave appears as a faint bright stripe. The stripe winds outward and fades. Its inner edge is sharper. Its outer edge dissolves into haze. The stripe suggests a past time when gravitational forcing was stronger or more organized. The sixth unlock rests in that fading. Migration changes not only where objects are. It changes how waves travel through populations. It can damp some patterns and amplify others. Over time, the disk becomes less like a smooth sheet and more like a set of surviving lanes. A final scale shift widens the view. Early migration may unfold over a few million years, which is brief compared to the system's age. The consequences can last for billions. A small early drift can define where stable neighborhoods exist today. The close of the section eases toward what comes next. The next step is to look at the long-term consequences of these moving boundaries for the overall stability of the solar system. The story shifts from how structure forms to how structure persists. Long-term stability is not a single promise. It is a balance between slow nudges and the system's ability to absorb them without crossing sharp boundaries. At this distance, the solar system remains stable, because most orbits stay far from the few pathways that amplify small changes into close encounters. A slow visual forms in a wide view of nested orbits. Each orbit is imagined as a faint, thin ribbon. Some ribbons are smooth, some show gentle waviness. Where ribbons pass near one another, the space between them is still broad. The first unlock rests in that breadth. Stability often comes from separation. When orbits are spaced with margin, perturbations act like soft background pressure, rather than sudden force. The section moves inward to a region where spacing is tighter. Two neighbouring orbits approach within a narrow band. Their ribbons nearly touch at one place. At that place, the ribbons have a slight thickening like a fog bank forming along a seam. The thickening marks repeated alignments. The second unlock follows. Tight spacing does not automatically cause instability. It raises sensitivity. The outcome depends on whether repeated alignments add coherently or average out. The system's safety depends on phase protection. A new term enters briefly. Phase protection is timing that avoids repeated close alignments. The phrase stays short. The idea returns to imagery. Two swinging lanterns can pass near each other without collision if their timing remains offset. The lanterns still swing. The gap remains. The importance lands softly. In orbital motion, offset timing can be maintained by resonances or by secular patterns. Without protection, the same near passes repeat and the gap can shrink. Another visual anchor settles on a resonance boundary. A ring-like lane in the asteroid belt looks clean. Next to it, a lane looks ragged. The boundary between them is sharp. Along that boundary, small clusters appear and fade like beads of frost forming along a cold edge. The third unlock rests on that sharpness. Stability boundaries are often narrow. Crossing one can change the long-term fate without changing the immediate appearance of the orbit. A body can look calm for thousands of orbits. It can still be wandering toward a boundary that matters on million-year times. A fresh analogy supports the idea without repeating earlier ones. A boat can drift slowly toward a sandbar in still water. The surface looks unchanged. The hidden depth determines when grounding happens. In orbital space, the depth is distance to a resonance overlap or a separatrix. The section deepens into the system's main stabilizers. Angular momentum is widely distributed. No single planet carries all of it. Mutual perturbations cause precession that can spread and decorrelate interactions. Dissipation in some subsystems can damp eccentricities. Together, these effects keep most bodies away from orbit-crossing states. The fourth unlock appears here. Many stabilizers are not walls. They are slow processes that keep the system from drifting into the wrong geometry. They act like gentle restoring tendencies. A single safe number anchors a central timescale without heavy math. The solar system has remained broadly stable for about 4 billion years, like a coastline that stays recognizable across countless tides and storms. The comparison keeps the scale grounded. The scale shift follows. 4 billion years is immense compared to an orbital period. It is also a finite window in cosmic time. Stability is real but not absolute. It is maintained by current architecture, not guaranteed by law alone. Another slow visual anchor appears near the outer system. A thin disk of distant bodies shows a sharp inner edge. The edge is like a cut line where density rises suddenly. Beyond the edge, a faint haze extends far outward. The haze has subtle clumps. The clumps are stretched into arcs by weak perturbations. The fifth unlock rests in this distant edge. Even weak forces shape structure when time is abundant. Small tugs from giant planets can sculpt distant populations, yet the vast distances also provide margin. Many paths remain stable simply because encounters are rare. Now a limit of intuition and observation enters softly and clearly. Long-term stability cannot be proven by observation alone because the timescales exceed any monitoring. A signal would be limited by the precision of orbital elements. Small errors grow under chaotic diffusion in some regions. Models can integrate forward, but they must approximate. They cannot include every grain of dust, every minor body, and every subtle non-gravitational effect. The limitation is incomplete initial conditions and finite computation horizon. Yet the sixth unlock follows. Stability can be assessed probabilistically. Regions of phase space can be mapped as mostly regular or mostly chaotic. Boundaries can be identified. The current orbits of planets sit in regular zones with wide margins. That placement is one of the deepest reasons the system persists. Another slow scene returns to the nested ribbons. One ribbon shows a gentle oscillation in eccentricity. The oscillation is smooth and periodic. It does not grow. Another ribbon nearby shows a similar oscillation with a slight phase difference. Their peaks do not coincide. The seventh unlock rests in those offset peaks. Secular coupling can distribute energy among modes. It can keep extremes from aligning at the same time. When extremes do not align, close approaches remain unlikely. The system stays in a regime where perturbations act like a slow breathing rather than a runaway push. A final scale shift widens to the full arc of time. Over centuries, stability looks perfect. Over millions of years, it looks like slow sculpting. Over billions, it looks like a selective filter that retains some structures and erases others. The close of the section eases toward what comes next. The next step moves from stability itself to the gentle meaning of stability. A calm perspective begins to form on how order emerges without any guiding hand, and how the solar system's quiet persistence fits into a larger cosmic context. A stable orbit is not a frozen track. It is a moving compromise among forces, and the compromise leaves patterns that can be read in light and shadow. At this distance, the solar system's order is visible as repeated geometry. Geometry returns because the underlying motions are constrained. A slow visual forms across a dark sky where a star sits at center. Several planetary orbits appear as thin, faint rings. Each ring is slightly elliptical. Each ring is tilted by a small amount. The rings overlap in projection, but not in space. Where rings cross in projection, nothing collides. The first unlock rests in that calm mismatch. Stability is three-dimensional. Apparent crossings can be harmless when planes and timing differ. The section moves to a closer view of one orbit. The orbit is traced by a dim ribbon that brightens near closest approach to the star. The ribbon then fades outward. The brightness change suggests a gradient in speed, faster near the star, slower far away. The gradient is smooth. It repeats. The second unlock follows. Repetition is a signature of stability. When the same gradients and turning points return without drifting into new extremes, the system is staying within its safe bounds. Two core concepts guide this section. Phase structure keeps close approaches rare. Secular cycles move energy between eccentricity and inclination without blowing up. A new term enters briefly. A secular cycle is a slow exchange of orbital shape and tilt. The phrase stays short. The idea returns to imagery. A slow tide can raise one shoreline while lowering another. The ocean does not need to leave the bay. In orbital space, eccentricity can rise while inclination falls. Then the trend reverses. The importance lands softly. The system can vary and still remain stable because variation is organized into cycles. Another visual anchor settles on a planet casting a shadow across a thin ring of dust. The ring is not a solid band. It is a sparse sheet. The shadow cuts a dark wedge. The wedge has a sharp leading edge and a softer trailing fade. As the planet moves, the wedge slides. The wedge returns with a slow drift in orientation. The third unlock rests in that drift. Precession shifts the direction of an orbit's ellipse and the line of nodes. The shifts are slow. They prevent repeated alignments from stacking in exactly the same way. The system avoids a single persistent bad geometry by rotating the geometry itself. A fresh analogy supports this without repeating earlier ones. A lighthouse beam sweeps a coast. Any one spot is lit only briefly. The sweep prevents constant glare in one location. In orbital dynamics, precession is the sweep. It spreads gravitational attention across angles. The section deepens into the quiet boundaries where order and disorder meet. Some regions are regular, their cycles are smooth. Other regions are chaotic, their cycles wander. The transition can be narrow. The fourth unlock appears here. Chaos can exist inside an overall stable system. Chaotic does not always mean imminent collision. It can mean sensitive dependence within a confined zone. Motion can be unpredictable in detail, yet bounded in range. A single safe number anchors a timescale of bounded wandering. A chaotic angle can drift noticeably over about 1 million years, like a slow hand on a clock that does not repeat the same minute marks. The comparison keeps the scale gentle. The scale shift follows. 1 million years is vast compared to a year. It is still small compared to the system's age. Bounded chaos can persist through many such spans without turning into catastrophe. Another slow visual anchor appears in the asteroid belt. A band of debris shows alternating bright and dim lanes. The lanes have crisp edges. Between edges, the density rises and falls like shallow dunes. The crisp edges are boundaries in orbital elements. Some are resonance gaps, some are stability islands. The fifth unlock rests in the crispness. Boundaries are maintained because unstable orbits clear themselves over time. What remains looks sculpted. The sculpting is not a single event, it is continuous filtering. Now a limit of observation enters softly and clearly. These patterns can be seen only indirectly. Most orbits are inferred, not watched as glowing rings. A signal would be limited by distance and by the faintness of small bodies. For distant populations, only partial arcs are observed. Short observational arcs produce uncertain orbits. Models must fill in gaps, they must extrapolate beyond the data. The limitation is incomplete coverage and finite precision. Yet the sixth unlock follows. Even indirect measurements can reveal stable structure. Gaps, clumps, and resonant groupings appear repeatedly across different populations. The repetition suggests underlying constraints. The constraints arise from gravity and timing. Another slow scene returns to the planet and the dusty ring. The shadow wedge now meets a region where the dust density changes. The wedge becomes darker. The change implies a denser sheet. The denser sheet lies in a stable zone. The seventh unlock rests in that density contrast. Stable zones accumulate material. Unstable zones lose it. Over long time, stability becomes visible as where matter lingers. The section eases outward to a wider perspective. Stability is not silence. It is a kind of low-volume music. Many notes change slowly. The chord stays. The last scale shift widens to the calmest possible view. From moments to eons, the same constraints guide motion. The close of the section points gently forward. The next step is a final settling. The last section gathers the arc into a quiet understanding of why stability matters and how the solar system's order can feel like rest. In the quietest view, stability is not a mystery. It is the gentle fact that motion can repeat without breaking its own boundaries. At this distance, orbits stay stable because gravity and timing shape a self-consistent pattern that resists drifting into dangerous alignments. A slow visual opens on a broad dark plain where faint dust hangs like mist. Through the mist, many paths are suggested as thin arcs. Some arcs are brighter where particles linger. Some arcs fade where motion is quicker. A soft gradient spreads from the star's glow into deeper night. The first unlock rests in the gradient. Where gradients are smooth and repeated, the system is not being shocked. It is being guided. The guidance comes from constraints that act every moment, not from rare events. The section settles into 3 core ideas. Conservation keeps overall motion from vanishing into noise. Resonant timing organizes repeated pulls. Chaotic regions exist, but many remain bounded. A new term enters briefly. Conservation is a quantity staying constant when no external work occurs. The phrase stays short. The idea returns to imagery. A sealed hourglass does not lose its sand. Grains move. The total remains. The importance lands softly, in orbital motion energy and angular momentum trade forms. The totals constrain how far an orbit can wander. Another visual anchor forms closer in. A planet's orbit is imagined as a pale loop. Along the loop, a thin shadow band appears where the planet passes through a sparse dust sheet. The shadow band is narrow. It repeats in the same place each cycle. Its edges are crisp. The second unlock follows. Repetition of a sharp feature suggests phase structure. When the same geometry returns, timing is staying coherent. Resonant patterns can keep closest approaches from occurring. They can also keep small bodies confined in stable islands. A fresh analogy supports timing without repeating earlier ones. A pair of pendulums can share a rhythm if a weak coupling keeps them aligned in phase. The coupling is gentle. The rhythm is persistent. In orbital space, resonance is the coupling. It locks a ratio of periods. It keeps certain angles from drifting freely. The third unlock rests in the word angle becoming a place. An angle is not just a number. It is a position along an orbit. When a resonant angle librates, the orbit's geometry has a preferred region. That preference can act like an invisible corridor that avoids close passes. The section moves outward to the asteroid belt again, but with a softer lens. The belt is imagined as a thin, dusty ring with gaps. The gaps are darker lanes. Their borders are sharp. Along one border, faint clumps appear. The clumps are stretched into small arcs. The arcs tilt slightly above and below the ring plane. The fourth unlock rests in that tilt. Inclination adds room. A system can be crowded in projection and still safe in 3 dimensions. Vertical separation acts like layered air currents. Layers can slide past with little mixing if they remain distinct. A single safe number anchors the vast scale of repetition without forcing arithmetic. A stable planet can complete billions of orbits over billions of years like a steady metronome that never needs to count its beats aloud. The comparison keeps the feeling calm. The scale shift follows. A single orbit can take days or decades. Billions of years contain more cycles than intuition can hold. Stability is the ability to survive that count. Another slow visual anchor appears at the system's edge. A distant population forms a faint shell. It is not uniform. It has a sharp inner boundary and a long thinning tail outward. The shell looks like breath on cold glass, brighter near the boundary and fading into darkness. The fifth unlock rests in the boundary. Even far away, stability leaves edges. Edges mark where perturbations become strong enough to reshape or eject. Inside the edge, objects linger. Outside paths are more easily altered by passing gravitational tides. Now a limit of intuition and observation enters softly and clearly. Much of this stability is inferred, not watched directly. A signal would be limited by distance and faintness. Short observation arcs can blur orbital estimates. Long-term integrations depend on initial conditions that cannot be known perfectly. The limitation is both measurement precision and model completeness. Yet the sixth unlock follows. Despite limits, stable structure is robust. Many independent clues align. Gaps persist. Resonant groups cluster. Planetary orbits remain well separated. These features point to a system that occupies a broad regular region of phase space. Chaotic zones exist near the edges. Many do not dominate the whole. The section eases into a final calm scene. The nested arcs are imagined again as ribbons in darkness. The ribbons do not tangle. They weave past one another with patient spacing. Shadows and highlights drift along them as if light is breathing. The seventh unlock rests in the word spacing becoming a principle. Stability is often margin. Margin is distance from boundaries that amplify. When margin exists, noise does not accumulate into crisis. It disperses into cycles. The closing settles without suspense. The solar system's stability is a quiet agreement between gravity and motion. It is renewed every orbit. It remains gentle across time. The tone softens toward rest. The next moment is not a new mechanism. It is only the same pattern continuing calm and complete.